All right, welcome back. Sorry I left you pretty much mid-sentence in the previous video. But I was saying that, again, to remind you of the different sizes of the particles that we're going to be dealing with to determine the soil texture. We're going to have clay-sized particles, silt-sized particles, and sand-sized particles. So any clay-sized particles are going to be when the diameter of the particle is going to be less than 0.0004 millimeters. And then just to give you an idea of how big a millimeter is, an inch is made out of 2.54 millimeters. So centimeters. So there's going to be 25.4 millimeters in an inch. So you can think of clay-sized particles as being absolutely tiny. You cannot really see them with your naked eye, meaning you can't see them without the aid of, a microscope or something. Okay, so silt-sized particles are going to be, and the diameter of them, I should say, are going to be anywhere from 0.0004 millimeters to 0.74 millimeters. So 0.74 millimeters is almost one whole millimeter. So you can almost see that. And let me correct that real fast before I continue on. So this should be 0.074 as well. Okay, forgive me for that. So again, silt-sized particles, although bigger than clay-sized particles, are also pretty hard to see. You can feel them for sure if you rub a bunch of them in your finger, like between your two fingers. It's going to be much easier to feel them, but it's not going to be able to. You're not going to be able to see them very clearly. And then for sand-sized particles, you're going to go somewhere between 0.074 millimeters to 2 millimeters. So 2 millimeters is much easier to both feel and to see, actually. So for the most part, anything in the sand realm, you can actually see with your naked eye. Okay? So we're going to do a couple of exercises to find the different types of soils textures that we got given the percentage of sand, silt, and clay. So let's go to that. Okay, so I have two different scenarios here where the soil that I have in blue is going to have 30% sand, 40% silt, and then 30% of clay. So let's start with that one. So I said 30% clay, this is the clay. So 30% clay, somewhere in that spectrum. I said 30% sand, so it's going to be, oh, I'm so sorry. Let's go back. 30% clay actually goes down this way. 30% sand is going to go down this way. And then 40% silt. So that one's going to go down this way. So we fall somewhere here in this clay loam area. Okay? That's pretty much the type of soil that we would get if we had this specific percentages for the particles in that soil. So now let's go ahead and do the same for the other percentages that I gave you. So if we had 70% of particles are made out of sand, 20% of them are made out of silt, and then 10% of them are made out of clay. Let's see what we get. So we said clay, 10%. Okay, sand 70%, so that's a little bit over here. And then silt 20%, 20%, so that's going to be over here. So we would end up getting this nice sandy loam, which makes sense. Okay, so if you're struggling with this, let me know, ask for help, and I'm sure that we'll be able to work something out. Okay? Because it is important. I'm pretty sure that I'm going to make you do this either in lab or in the test for sure. So now we're going to talk a little bit about water in soils, which is one of my favorite things. I actually studied hydrogeology for my master's, and so I did a lot of porous media flow. So this is one of my favorite things. But anyways, this water in the soils is officially going to be the moisture content within those soils. It usually increases the strength of a soil but only up to a point. Once there's too much water, it makes it unstable, and we have seen that in the past chapter, right? In the mass wasting chapter, if something is too saturated, it's going to be more likely that that thing will collapse. However, if it's very dry, it's also very likely that it will collapse because there's not enough moisture keeping all the grains together, if you would. This moisture content within the grains is also going to have a very large effect on shrinking and swelling of your ground, of what you have. So if you have a lot of water, it's very likely, depending again on your soil particles, but it is much more likely that your soil volume is going to expand because the water is percolated and inside the different pores within each particle. So if you have very little water, it is very likely that the air between those particles is now going to shrink. There's not going to be air anymore between the particles, and the particles are going to come closer together. However, if there's air or if there's water, it's less likely for the particles to come closer together because water is much harder to push than air. Okay, that's going to be important further on. So if there is water within particles, within those spaces between them, it's going to be harder for the grains above to push down on it, to basically shrink that space. If there's air, it's going to be much easier for those overlying particles to make that space shrink, okay? I want to also mention something else. If you think about these grains as being all rounded, like they're showing you right here, and kind of positioned in random spots, as you're seeing. If you think of grains that are fairly large, it's going to be less space in between them than grains that are smaller. However, overall, if you look at a mass that has a lot of them. However, if you look at the smaller ones, it is much more likely for them to be touching on different sides than the bigger ones. So let me draw that actually so you kind of get what I'm saying. Let's go over here. So if I have this very large kind of angular grain, 1, 2, and 3 grains that altogether have a specific weight, let's call it 10 pounds. And then I have, on my other scenario, a bunch of very small grains. It's going to take a while. That, are lying on top of each other, so they are touching each other pretty much everywhere. Anyways, if you think of this amount, just multiply it to cover the whole 10 pounds as well. Then the amount of water that can travel through, or it can be stored, and between the grains is going to be much larger. For the ones that are small, you're going to be able to store a lot more water throughout the whole volume where the smaller grains are than you are in this pocket. This pocket is going to be, although it looks big, it's going to be much smaller than all the smaller pockets from that volume. Okay? However, it is going to be much easier for the water to get through here, or here, or here in those big pockets than it is going to be for the water to get from this little pocket to this little pocket, because these grains over here are touching each other in almost every side. So it is going to be much harder for water to go, again, from a little pocket to another little pocket. So I'm going to give you the technical terms about that later on, but it's going to be basically porosity is how much space something is going to have, how much empty air space is going to have, and then permeability is how well connected that empty space is. Okay? And so that is going to be relevant further on, as I said. Okay, so now we get into our actual natural hazard itself, which is going to be subsidence. Okay, so that subsidence is pretty much going to have to do with the soil volume change that you have in the ground. So it's basically ground failure. It's going to be the sinking or vertical deformation of land associated with any of these things listed below. So that ground failure is going to be associated with either the dissolution of rocks beneath the surface, and that's going to be called karst topography, and we'll talk about that first. Also with ground thawing in places where you have permafrost, we'll also talk about that later, where you have compaction, and usually compaction happens when you don't have enough water filling up the gaps. When you have earthquakes, it makes things shake and move around and create new empty spaces. When you have the drainage of magma, which can happen in lava tubes, and we've talked about that a little bit when we talked about the volcanoes lecture. When you have withdrawal of underground fluids, and that's very much so caused by humans. I mean, rarely by nature, but most of the times by humans. When you have collapse of underground mines, definitely by humans, and it's a similar process to that drainage of the magma. And then you have the draining of marshes and of swamps, which is again also caused by humans for the most part. So those are some of the causes or the events that can happen, the processes that may cause land subsidence. And again, that land subsidence is simply going to be ground failure, and it has to do with the overall volume of the of the soil underground. So, as I was saying, it has to do with dissolution of those rocks beneath the surface. One of the processes is that the thawing of that permafrost, the expansion and shrinkage of the clayey soils. So again, for that, when we'll talk about that later, but it's going to have to do with the amount of empty spaces that are in clay soils versus the empty spaces that are, say, in sandy soils, and how that water is going to behave within those particular soils. So now you're thinking about space, water inside them, and the permeability, the way or the possibility for water to go from one pore to the next. Okay. It's also going to have to do with the decay of organic soils, so how fast that decay is, the compaction of the soils itself, with the groundwater removal, and with other geologic processes. And in that case, they're thinking things like, again, earthquakes or whatnot. Yeah, pretty much. All right, so the first type of subsidence that we're going to see, or the first process, is going to be the karst topography. So karst topography is going to come from the dissolution of rocks beneath the surface. So the example that we have down here is going to be an extreme case of karst topography. The one that you're seeing in the diagram over here is a more common one. And also the picture back here, this one, is pretty much a picture of the same diagram that you saw in the next slide. So if you look at the sinkholes, maybe over here, there's a ton of them, pretty much everywhere. They're analogous to what this diagram is showing you over here. And if we were able to see what the underground looks like from that picture, it would look something similar to what you're seeing in the diagram over here. Okay, so that dissolution of the rock happens due to carbonic acid kind of dissolving it, that chemical weathering that I talked about earlier in this lecture. But I'll go through that in the next slide. So how that carbonic acid actually gets inside the system is going to be through water. So either through surface water that runs on top of rocks that are susceptible to be diluted. That sounds funny, but yeah. And then it can also run through the groundwater, which is the case for most of the sinkholes that we see, most of the karst topography that is formed. So acid water is pretty much going to run in the groundwater, and whatever the groundwater is touching, if it is touching a material that can be dissolved, then it will do so, and it will start creating those empty spaces where that material used to be. So it affects, for the most part, rocks like carbonates. So in the realm of carbonates, you're going to have things made out of calcium carbonate. So there's going to be limestones, dolostones, or marbles, which again, marble is going to